So principal stresses and principal planes continued. So yesterday we had looked at the how to find out the principal stresses uh, and the directions of the principal planes through the solution of an eigenvalue problem. Now we had also depicted that the principal stresses come out to be the extreme values. Okay, so sigma average plus r and sigma average minus r. Now, because these are extreme values, it gives us an indication that perhaps in the same way that we learned how to maximize functions, we could probably arrive at the same result. So, what we want to do here is we will take a relook at the expression of the principal stress, or rather the transformed expression of the normal stress, which is this. So an alternative way of looking at the principal stress. So this is the general stress transformation formula that we have learned. If you look at yesterday's notes, you will see this: sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2. What was it? Cos 2 theta plus tau xy sin 2 theta. So the idea here in this alternative way is to see that perhaps if we differentiate this sigma x dash with respect to theta, then maybe we'll find something useful. So since the idea is to move towards extreme values, what we'll do is we'll employ this particular condition. So from here, what are we going to get? Minus 2 sin 2 theta. So and from that, right. So from here, if we proceed, we'll obtain for tan 2 theta this is the expression we obtain. Now please compare this with the result that we had obtained from the eigenvalue problem yesterday. Is it not the same? So it is exactly the same thing. So this gives us an indication that the principal stresses that we are going to obtain, those are indeed the extreme values. Okay, but there is a catch here. So everyone listen very carefully. This is not to be found in certainly not in Beer and Johnson and not in any other standard textbook. And believe it or not, I also came to know because one of your seniors many years ago, I think it was he was from the batch of 2017 or 18, 17 ME or 18 ME. So he had asked a question, and then I dug deeper. I found this out, that although usually what happens is that the principal stresses are the extreme values of the stresses, but it is not necessarily so always. In the most general situation, it is not going to be so. So what is not the most general situation? So we are working under the condition that tau xy is equal to tau yx, tau yz is equal to tau zy, all those things. There are certain kinds of materials which when they behave, okay, so this condition doesn't hold true because there are something called body couples present. Because of the presence of those body couples, the moment balance is not satisfied the way you had learnt it in BEM, in basic engineering mechanics. So tau xy is not equal to tau yx, tau yz is not equal to tau zy for those kinds of materials. Now when that doesn't happen, when that tau xy is not equal to tau yx, then there is a clear distinction between the principal stresses and the maximum and the minimum stresses. Okay, so there is a clear distinction. Now, this is of course absolutely beyond the scope of what you are learning, so no need to worry. Yes, the Moore circle gets shifted up a little bit. Okay, so maybe you should ask ChatGPT this question, see if it can answer. Not now. All right, so we have obtained this. Now, what we want to see, so all this while, whenever we are talking about principal stresses, please note that we are only talking about the normal stresses. But we also have the shear stresses, right? We have not talked anything about that, whether they are maximum, minimum, what happens to them. So we want to investigate what happens, or if you could actually obtain the maximum possible values of the shear stresses. Okay, so what do we do? So for that, we are not going to do any eigenvalue problem. Rather, we are going to go down this particular route, which we have chosen as an alternative route for investigating the principal stresses. Okay, so maximum shear stress. So what was the expression for the tau x dash y dash? Please go back to your notes and tell me. Something like tau xy cos 2 theta. Then plus or minus. Was it plus or minus? If it is sigma xx at the, so I believe it is something like this. Right. So everyone please check with your notes from earlier. Right. And now in exactly the same fashion that we had investigated this principal stress, we are going to do this. This is equal to 0. So that gives us what? So this one gives us minus twice tau xy sine 2 theta and minus sigma xx minus sigma yy by 2 cos 2 theta. So from here, what we obtain is this. So tan 2 theta, that is going to be equal to minus sigma xx minus sigma yy by 2 tau xy. So in order to distinguish between the angles which correspond to the maximum shear stress versus the angles which correspond to the maximum normal stresses, we will use the subscript as before for this principal stress P and for the shear stress S. Okay. Now can you observe something very interesting? If you look at the expression of the tan 2 theta P and this tan 2 theta S, if you multiply them together, what is the result? Minus 1. Okay. So it is minus 1. Okay. Which means that there is a difference of angle pi by 2 between the twice theta P and the twice theta S. Okay. So all right, which means in terms of the actual angle, the theta P and the theta S, there is a difference in angle of 45 degrees. Okay, let me write this explicitly. 45 degrees. Fine. It is an interesting result, but it is of tremendous usefulness in actual engineering practice. And later on, when you do labs, this will actually be very clearly demonstrated to you when you do the tensile test versus when you do the torsion test. And there is actually a little thinking type of question at the end of the tutorial sheet number 6, okay, related to this. Now, uh, what we want to very quickly do is to check that if this is indeed the angle corresponding to the maximum shear stress, then what is the expression of that maximum shear stress? Because what you have only obtained here is the indication that at what angle the maximum shear stress will be oriented. But what is the expression of the shear stress, maximum shear stress? Okay, that we want to take a look at. If you look back at the Morse circle, what do you think is the maximum value of the shear stress? Take a look at the Morse circle, go back. It is? Yes. So the maximum value of the shear stress, that is nothing but the radius of the Morse circle. Okay. So let's check now through the algebra whether that is actually validated or not. We are again going to take up this particular expression itself, this tau x dash y dash, and here we are going to carefully substitute the expressions for the cos twice theta and the sin 2 theta. So tan twice theta s, that we have obtained as minus of like this. Okay. So what we'll do is this sine twice theta is, if you just look at it, you are going to get and there is a square root. Right. Okay. All right. Similarly, oh, yes. So cos twice theta is, it is going to be if you have any confusion with these two expressions, please tell me. It's just algebraic manipulation, okay? All right, now that we have these two things, what we can do is we can quickly substitute them in that expression of tau x dash y dash. So this cos 2 theta is, I'll have By the way, please note that this entire thing in the denominator is nothing but the radius itself. Okay, this is nothing but the radius itself. So cos twice theta is, that will be tau xy divided by r, and over here I have this thing, and now sine twice theta is, that will be so you see what is happening here. What is the thing in the numerator? R square. So this is r square divided by r. So that is nothing but r. Okay. So whatever we had expected from the Mohr circle, this is getting validated. Okay. But please note that whatever we are doing, it is within the xy plane. So when we write this thing, this maximum shear stress, please understand that this is actually what is referred to formally as the maximum in-plane shear stress. Okay, maximum in-plane shear stress, which means that there should be something, the maximum, I mean the overall maximum also, which is not just the maximum in-plane shear stress. Okay, so what is that thing? Now to understand that, we have to go through some intermediate steps. Okay, the formula is very easy. You don't have to worry about new formulas and new theories coming up, but there is a little bit of a conceptual thing going on here. So please remember this. Now, whatever we do after this will be like an application of the theories which you have already developed towards understanding some concepts which will be extremely useful for solving problems and certainly for your professional practice. Okay. See, all of these is under the purview of the plane stress condition which we had described earlier. Okay. Now, in plane stress, what do you have? You have, in general, non-zero values of sigma xx, tau xy, as well as sigma yy. These are, in general, the non-zero values. They can be zeros, but in general, they are non-zeros. But what you require via the application of the plane stress condition is that sigma zz should be 0, tau zx equal to tau xz should be 0, and tau yz equal to tau zy equal to 0. This we have already mentioned earlier. Now, let us take a look at a very common kind of stress element depiction, which you will most often see in many textbooks. The reason I am highlighting it like this is that till now we have not drawn any stress element. Maybe in your basic engineering mechanics you have drawn some stress elements. So what I mean to say here is that usually it is depicted like this, that you have something like a square or a rectangle, and then on both sides of it, it is written like sigma xx. This is sigma xx, this is sigma yy, this is sigma yy, and then here you have, this is tau xy, this is tau yx. So let's write it like that. And this is tau xy. This is the general depiction. Which direction is the z direction? Pointing out of the plane. Okay, pointing out of the board is the z direction. Okay, before we discuss anything regarding the z direction, please note that in general you will be given numerical values of this sigma xx, tau xy, sigma yy. Through those specifications of the three values, you will be able to find out the stresses in any direction. What is the meaning of that sentence? All this while deriving our various things, our stress transformation formulas, we have not drawn this stress element. What did we do? We took a point like this. And then we said that we will take a plane like this. This is the cutting plane. Okay, maybe there is a body like this. This is the point in which we are interested. We have taken a cutting plane. And then over here we say that there is a unit outward normal which will be in the x direction. If you choose the x direction like that, this will be the y direction. On this there will be a traction vector, and the components of that will be sigma xx, tau xy, all those things. Now if you take this picture, then what happens is that if I don't draw the traction vector, rather I just write like this, sigma xx, here I write tau xy. This is from the right hand side perspective. From the left hand side perspective, it is just going to be something like this. This is sigma xx, this is tau xy. Okay. Now, if I take another plane like this, okay, if I take another plane like this, perpendicular to that plane will be the sigma yy. Shearing will be like this, tau x, tau yx, all those things. Now you can imagine what kind of a cluttered picture this is going to be, even in 2 dimensions, forget 3 dimensions. It is because to avoid this kind of a cluttered picture that people use this kind of a picture. Okay, so the idea here is that whatever this side and this side of the plane is, that is understood by this line and this line. It does not mean that we have taken a solid chunk of material out, okay, and on the right hand side is sigma xx, on the left hand side is sigma xx. It does not mean that. Okay, so this diagram is just a proxy for this diagram, okay, which is very, very difficult and cluttered and confusing to draw. Please understand this very carefully. It is extremely important to understand this because there is another topic called stress equilibrium, where again we are going to draw this thing, but this sigma xx on the right hand side and the sigma xx on the left hand side, they are not going to be equal. Okay, there we are actually considering a certain width dx or delta x of this material. Okay, so there is a clear cut distinction between the two. It took me quite a while when I was a student to figure this out. Yes?
There is no difference with pulling the dx to 0 or something.
It is not. So this one, here there is no dx.
If there is a dx and a dy, if you swing dx and dy to 0, then is the...
No, it makes a world of difference. It makes an absolute world of difference. We'll do that. Okay, we'll do that later. Acha. So here we understand that this is only a proxy for this. Okay. Now, this is easy to understand. This is just a diagram. But now suppose I tell you that this particular tau xy is equal to 0. Okay. Tau xy is equal to 0. Suppose I say that. Furthermore, in the plane stress condition, we already know that tau xz is equal to 0. So this is given, tau xy is equal to 0, it is given to us. And by the plane stress condition, we know that tau xz is automatically 0. Now what is happening? You look at this plane or this plane, whatever, and now you tell me what is the physical situation now? Isn't it a condition where all the shear stresses are 0? Tau xy is 0, tau xz is 0. Okay, so if you have that kind of a situation where the shear stresses are 0, what is the normal stress called? Look back at your notes. I'll repeat my question. Principal stresses. Okay, so the shear stresses are 0. Tau xy is 0, tau xz is also 0. If they are all 0, then the normal stress which is there, the sigma xx, this itself is the principal stress. This itself is one of the principal stresses. Because if you look back at the fundamental definition of the principal stress where we looked at it, what was the definition? It is such a plane, the principal plane is such a plane on which the traction vector itself is oriented along the unit outward normal. Traction vector oriented along the unit outward normal means that there is no shearing component of the traction vector. And when there is no shearing component of the traction vector, then you do not have any shearing component of the stresses also. Okay, so which is why in this kind of a situation, you have this stress element, the traction vector indeed is like this. This is the n hat, oriented along the n hat itself is the traction vector, and the traction vector has no opportunity to contribute anything in the shearing direction, either in this thing or out of the plane. Okay, so please always keep your eyes and ears open to identify this kind of a situation. Maybe you do not even have to go down the route of the eigenvalue problem. Okay, you do not have to extremize anything. Just by the specification of the stress values, you can figure this out, whether the normal stress itself is the principal stress or not. Now, if you think you have understood it, you tell me something. On this surface, this also is a plane. You have understood that this is a plane, this is a plane, this is a plane, this is a plane. But this also is a plane. This is the most obvious plane staring at you. On that plane, what is happening? So on that plane, you have sigma zz equal to 0. What else is 0? Tau zx equal to 0 and tau zy equal to 0. Right? What is the conclusion from this? Sorry? Think. This is a trick question. Sigma zz is 0. Tau zx equal to 0, tau zy equal to 0. We have just now seen that if the shearing components of the stresses are 0, then the normal stress component will be one of the principal stresses. Forget the Mohr circle. You tell me about, is there anything special about the sigma zz equal to 0? Exactly. Very good. That is the correct answer. So see, so on this plane, okay, so on this plane, what do you have? Sigma zz equal to 0, tau zx equal to 0, and tau zy equal to 0. Because these two things are 0, okay, because these two things are 0, therefore this one is a principal stress. It is 0. Sigma zz is equal to 0, nothing is disturbing it. But that 0 value itself is one of the extremum values. Okay, the 0 value itself is a principal stress. This is like if we have a probability distribution of various kinds of mistakes that have been done by your seniors, this would be having an extremely high peak. Like half the class or probably more than that gets it wrong. Or even if they know it, they forget it while doing the problems. Okay, so sigma zz equal to 0 is also a principal stress. Very, very important. In the tutorial sheet, I have given a problem where step by step I have asked you to go from that two-dimensional Mohr circle that we have drawn in class to a three-dimensional version of the Mohr circle. So in that three-dimensional version of the Mohr circle, you will be able to see, I think you have the tutorial sheets, right? Rohit, can you give me one sheet? I can tell the question number maybe. Thank you. So the question number that I'm referring to is question number 10. One entire page of question. Okay, but that is only because I have given you all the intermediate steps that you have to go through. So in this question number 10, ultimately when you do it, you will find that there are three circles. That is what is referred to as the three-dimensional Mohr circle. It doesn't mean that you have to draw circles or spheres in 3 dimensions. It's just that you have to draw 3 circles. Okay, and you will be identifying 3 principal stresses.
What is
Let me finish. So in that kind of a situation, that sigma zz is equal to 0 will be also one of the values. Yes, Charit.
So what is the condition in which sigma is equal to 0 and tau has some maximum value?
You want to find out the
We found the upper point of Moore circle. What is it? Fuse here.
So what Charit is asking is a very important question, that suppose we consider this Moore circle, this two-dimensional version itself. So we have understood that here we have one sigma p1, here we have another sigma p2. Sigma p1 is equal to sigma average plus r, and sigma p2 is equal to sigma average minus r. Now Charit is asking that this point where we have the radius is 0 and this is the maximum possible value of the shear stress, because remember that this is the tau x dash y dash and this axis is the sigma x dash x dash. So this is the peak point of the circle. Here you have the maximum value of the shear stress. So what is the value of the normal stress corresponding to this? You see yourself, what is it? What is it? This one? Yes? This one? Sigma average you are saying? Yes, sigma average. Right. So, yeah. So, you will have the sigma average value, okay, for this thing. So, this point will be sigma average comma r. Okay, it is not 0. It will be 0 in which condition? So, this is a multiple choice question. Tell me, when is the normal stress corresponding to the maximum shear stress going to be 0? When sigma average is 0. When is that? When the center is at the origin. When the center is at the origin, what is happening to the sigma p1 and sigma p2? They are equal and opposite to each other. Okay, they are equal and opposite to each other. Very good. Now, let's discuss regarding these things, that this 45 degrees and 90 degrees things that we have discussed. Let's look at them geometrically. Earlier we had seen that the principal planes one more thing, very, very important, and I'm glad that it is going on record. This is principal, P-A-L. Okay, principal means it is main or extreme. It is not. Okay, this is wrong. Okay, it is not principal. What is principal? It's a man of principles. Okay, something which the VP should not be, right? That is the criteria. Okay, we all understand what we mean here. So so maybe I'll cut this out. So no, I mean 2 years or maybe 10 years down the line, the VP will be in a position where he'll give lots of money to IIT Kharagpur. I don't want to piss him off. They go on to become big shots. So principal is different, okay? So principal. All right. Now principal planes, we have seen that the angles are given by theta p and theta p plus 90 degrees. What is the implication of this? Suppose we look at the stress element itself. Okay, we are looking at the stress element. Now in general, so you have set up your coordinate axis like this, that this is x, this is y, this is sigma xx. You don't know anything about it, okay? This is a general state of stress which is given to you, sigma xx tau xy, and maybe here also this sigma yy is also given. I'm not drawing its brothers and sisters, okay? Okay, so those are there. I'm not cluttering the diagram. Now, theta p means that if you rotate this stress element by the theta p, you will obtain a plane on the right hand side such that on that plane the normal stress will have an extremum value. Okay, so what I mean by that is this. So yesterday, when we were talking in terms of traction, we considered this, right? This was the plane to begin with, this was the point. And we took an arbitrary cutting plane like this. On this plane, if the traction vector turns out to be oriented along the unit outward normal, then that yellow colored plane which we call as the principal plane. We all understand this. It is that diagram only which I am trying to redraw here, except now what I am trying to do is around this point I have drawn this little stress element. So around that yellow colored point, yellow colored plane also I can draw a stress element. Just that. Okay, so if you accept that this is the usual plane and this is the plane on which this is the principal plane, then this also is the principal plane. This edge of the stress element, that is the exact thing which I am trying to draw here. So this is my point of interest. Around that point I get another rotated stress element. Okay, on that rotated stress element, what I will have here, this thing is sigma x dash, but because there will be no shear, this thing itself will be equal to the sigma p. Okay, for this to be sigma p, please note that the value of the tau x dash y dash on this thing, that is going to be equal to 0. It is absolutely necessary. Okay, but then what is the implication of this theta p plus 90 degree? See, we have oriented, so the angle between these two things, this is our theta p. So theta p plus 90 degree also should be such a principal plane. Where is the theta p plus 90 degree? Theta p plus 90 degree is this plane itself, is it not? Because this is a square. If you rotate this square further by 90 degrees, this edge will coincide with this edge only, na? Is it not? Clear? Everyone? So this edge is going to be coinciding with this edge. So on this edge only we'll look. So on that edge, what is the thing? There will be another normal stress. Okay, there will be another normal stress. So that thing will be also sigma p. But we have already seen that we are getting two values of the sigma p, right? Sigma average plus r, sigma average minus r. So one of them will be the sigma p1 and the other will be sigma p2. Please do not have any bias which one will be the sigma average plus r and which one will be the sigma average minus r. It is only by doing the actual calculations you'll be able to find that out. In the very first problem of the tutorial sheet, there is such an exercise. Okay, exactly the same thing that you have to do. Okay, so when you do that, it will be clear. Okay, now let's talk about that 45 degree business. Where is that 45? Right, theta p minus theta s. Okay, so we understand that this yellow colored rotated stress element is where you will have the principal stresses. But now it is time to consider the shear stress. Okay, so we'll draw it separately. Now, since you guys are quite good in geometry, what I'll do is I will ask all of you to tilt your head in the direction of this yellow colored stress element. Okay, so we are all in line with this. Okay, so you tilt your head so that we are looking at it like this. This is our stress element where the edges are oriented along the principal planes. Okay, I am not going to draw this white colored original stress element. Okay, because if you draw it here, that will look rotated clockwise like this. Okay, but what I want to draw now through a separate color is another stress element on which I'll be able to show the maximum shear stress. Now, using that information, theta p minus theta s is equal to 45 degree. Can you guide me how to draw it? So let me orient the axis first. This, mind you, is not x-axis. This is not the x-axis. This line depicts the unit outward normal to the plane, which is the principal plane. That's it. So from 45 degrees to it, or at 45 degrees to it, I'm going to have something like this. Okay, maybe I should draw it darker. Now, I want to draw a stress element whose one of its edges is perpendicular to that thing. So it is going to look like this. This red colored, okay, this rotated red colored stress element is where you are going to have the maximum shear stress. Okay, so if I draw the shear stress here, this tau, this is the maximum in plane shear stress. Okay, so this is the maximum in plane shear stress. Yes. Yes. Sorry? You don't believe this is 45 degrees? Huh? See, it is 45 degrees. Now you believe it. Yes.
Can we see the theta p and theta s in more circles?
Can you see the theta p and the theta s on the Mohr circle? Yes, you can. But I have to have another discussion regarding that. I want to finish up other things. Let's see if we have some time. Maybe we'll go down that. Okay, now tell me, it is very tempting to say something here. Everyone, please listen. Sir. So on this, what you have is the sigma P1. And when you have the sigma P1, you can rest assured that the corresponding shear stress is going to be 0. So on that yellow colored edge, the shear stress is 0. Now we have understood that on this red colored edge, the shear stress is the maximum, at least within the plane. But now the temptation is to say that correspondingly, the normal stress is 0. Yeah, but normal stress is not 0. Okay. So just because you have this thing as maximum, please do not jump to the conclusion, the wrong conclusion, that the normal stress on that edge is 0. It is not. Okay. You can have certain situations like that, but in general, it is not going to be like that. Okay. This is very, very important. Now tell me something. This is the maximum in plane shear stress. Suppose I draw this, because you understand that no matter how much we rotate, once we choose a stress element, that particular stress element should be in equilibrium. Okay. So this thing is what? It is tau only. Okay. It is tau only. Now you are saying it so very obviously, it is tau only. But see, there is a nice implication of what you have so obviously concluded with what you have already obtained earlier. Please note here, tan twice theta s is equal to minus sigma xx whatever. So suppose to begin with, you are supplied with certain values of sigma xx, sigma yy and tau xy. You are going to obtain a certain value of this twice theta s. But then this is a tan, which means that you are also going to obtain the same value, the same numerical value of the right hand side if you substitute twice theta s plus 180 degrees, right? Which means that theta s comma theta s plus 90 degrees are both the solutions. Okay, they're both acceptable solutions. Okay, so from here we can write that theta s is one solution and theta s plus 90 degrees is another solution. Both of them are acceptable solutions. And very much in line with that, you see, if this is a solution tau, then at 90 degrees to it, because if this is the unit outward normal, you rotate that outward normal by 90 degrees. On that also there is a shear stress which is maximum. Okay, so everything is connected and I mean it is in sync. Okay, now you tell me, taking inspiration from the fact that um, the maximum shear stress is the radius. Okay, the maximum shear stress is the radius. I will draw the Mohr circle once more. You tell me something. We have understood that this here is the tau max in plane. But is it possible to write an expression for this tau max in plane in terms of the sigma p1 and the sigma p2? You see, this is the sigma p1 and this is the sigma p2. My question is, can you write the tau max in plane is equal to something something involving the sigma p1 and sigma p2? Exactly. So the tau max in plane is nothing but sigma p1 minus sigma p2 by 2. Okay. Now, as I have told you a few times earlier, that when we are talking about shear stresses, it doesn't make much sense to talk about the positivity or the negativity of it. As long as we have an understanding of its direction. So in reality, what is written is that, because in general you do not know whether sigma p1 is larger or sigma p2 is larger. Here in this diagram, because I have obviously drawn it like this and I have labeled it like this, that's why you think that sigma p1 is larger than sigma p2. But when you are doing a problem, you do not know. Okay, so it's better to write this as an absolute value. Okay, because that depicts that it is actually a radius. Okay, with a positive numerical value. So sigma p1 minus sigma p2 by 2. Now the trick question is as follows. Tau max in plane is equal to sigma p1 minus sigma p2 by 2. What do you think will be the overall tau max? I will point to this diagram, where I gave you a hint regarding this zero stress also being a principal stress. Okay, so what I'm trying to tell you here is this. You have one pair of principal stresses here, sigma p1 and sigma p2. But there is a hidden principal stress which we are not depicting in this diagram, which is the sigma p3 equal to 0.
Sigma p1 by 2 is sigma p1 by 2.
Okay, so sigma p3 equal to 0 is a hidden principal stress. Sigma zz equal to 0 is also a principal stress. It's like a hidden principal stress. So if I ask you that what is the tau max absolute, the overall tau max, then what do you think it will be? It will be equal to sigma p1 minus 0 by 2. Okay, or it is better to write something like this. Yes, exactly. It will be the maximum of sigma p1 minus 0 by 2 comma okay, comma one of these things. Now, some of you may be a little bit confused regarding these two options. How can these two things even be an option? Okay, I am considering the case where sigma p2 is larger than sigma p1. That could be a case. Okay, but if you arrange the values of your principal stresses such that sigma p1 is always larger than sigma p2, then this is not an option. Okay. However, there is a catch. Okay. See, suppose your stresses are like this. Okay. So, I'll give you a break, don't worry. Suppose this is like this 10, 5, and this is always 0. Okay. Then the tau max absolute, that will be what? It will be 10 minus 0 by 2. Okay, this is the tau max absolute. If this is, let's say 10 minus 5, 0, then what is it? Then it is 10 minus of minus 5 divided by 2. Okay, but it could also be something like this, that you have, this is 5, this is 10, and this is 0. Then of course this is like this. Okay, so you have to be careful. Okay, don't just blindly go with the sigma p1. Take out the actual maximum value and do this. Now you are also going to encounter certain situations where this sigma zz is not 0. Okay, meaning that you are no longer confined to the plane stress condition. Plane stress condition is an important class of problems, but it's not. I mean, there are classes of problems which are beyond plane stress also. In which case, sigma zz is not going to be equal to 0. Okay, and then you will have to do completely separate kinds of things. All right. So let's conclude here.